Well, g'day. It's a shame that we're here back in our lockdown situation, but here is a video on multiplying matrices and powers. It's what I intended to do this Monday and Tuesday, and I'd like you to have a go at it yourself, but then we will cover this again. We'll have some time to review it once you're back at school. So don't worry too much, do the best you can. Make sure though, most importantly, that if you don't understand something, pop me an email, jump on the Teams, ask me questions as you need to. So multiplying matrices and powers. Learning goals there, using matrix multiplication, that is multiplying matrices by each other and hence using powers. That's the goal for today and for tomorrow. So we already created matrices. I've defined a couple there, A and B. They're two matrices which I've just randomly defined, so I'll just go to my highlighter, here and here. And we know that we can use matrices to store things. And we know that a matrix has a dimension. Both of these are 2 by 2. We also know that matrices have elements. So there's 4 elements in each of these matrices. And they can store real information or they could be theoretical. We've added and subtracted matrices. So over here in light blue, you can see I've done A plus B. And because they have the same matching dimensions, I can add them together, it's okay. And I just add together the equivalent parts. 20 and 40 make 60. 15 and 16 make 31. So we've done that before as well. And we've also multiplied matrices by scalars. So you can see here in orange, 3 times A is equal to 3 times the matrix A, which is equal to 3 times 20, 3 times 15, 3 times 10, and 3 times 25. All these things we've done already in class, and you've had some practice at. If any of them you're unaware of, you're unsure of, go back and practice those again. They're really important for what's coming up. So now we're going to multiply matrices together, because previously we've multiplied by a number, a scalar. Now we're going to multiply matrices, A times B, or we can write that as AB. So let's have a look at what we think. And this was meant to be a thinking exercise. This is meant to be me just checking out what you thought about this. And I'm guessing now that's not going to happen, but let me have a guess. If we had a calculator, I'm guessing you might think that this, I won't do this yet, I'll do 20 times 40, and 15 times 16, and 10 times 21, and then 25 times 35. Now I don't have a calculator, but I'll do my best. This one here gives me 800, I believe, and 15 times 16, I believe, is 240. 10 times 21 is nice and easy, that's good. And 25 times 35 is 875, I believe. So there's our new resultant matrix based on that operation. Now it turns out that matrix multiplication is actually very humanly defined. So we've just created the system that is matrix multiplication. And we've created it to suit a whole bunch of different contexts. Reasons why we might multiply matrices together when you've got some matrices that are storing information or are steeped in context of some sort. In this case, there isn't really any context that suits this type of multiplication. Multiplying two matrices together like this, if they're storing information, these numbers don't actually have any meaning. So this is not how we multiply matrices together, because it doesn't actually help us to solve problems or complete processes within the systems that we use matrices. So instead we've got another system. So this is the first thing I want to do in this video. I want to wipe out the misconception that this is how we multiply matrices, and it's a common mistake, even after we've taught this. So if you can get this right, you're already one step towards getting some really nice bonus marks, particularly in complex familiars in your exam. So let's have a look at what it really is. Let's consider a show bag quickly, and this is a bit of context. So if you want to pause the video now and have a think about what I've just said, now would be a great time to do that. So let's consider a simpler example, show bags, because the Gold Coast show is coming up, although maybe it's not, who knows. Andy's all chocolate show bag contains 10 Mars bars and 7 cherry ripes. Just read this line here. Graham's chocolate galore contains 5 Mars bars and 11 cherry ripes. That's that line there. When creating their show bags, the cost for each bar is 55 cents for Mars bars and 65 cents for cherry ripes. Each bag sells for $12. Who makes the most profit? Okay, so there's our question. Now, this is a pretty simple example. I've designed it that way. See, we don't need matrices. And you're probably thinking, I don't need a matrix for this, because Andy has 10 Mars bars and 7 cherry ripes. That's 10 times $0.55, 7 times $0.65. That's $10.05 for Andy. Should pop a little dollar sign there, shouldn't I really? And Graham, he's got 5 times 0.55 and 11 times 0.65, that's $9.90. Graham clearly makes the most profit, and I can do that little subtraction as well. So I can say, well, 12 minus 10.05, well, that's equal to $1.95 profit, or 12 minus 9.90, that's equal to $2.10 profit. So I can work out the profit. Problem solved. Who needs matrices? Go away, Mr. Manson. Well, let's take a step back from that, because when we get bigger problems, matrices could save us time. And a computer, in particular, is going to have trouble interpreting what's written there. Although they are getting better and more intelligent in that respect, but they're going to have trouble interpreting that. But we can give a computer matrices easy, and the computer can operate on matrices easily. So this is one reason why we might do it. If we've got a lot of data, let's say all of the different types of chocolates that are in all the different types of show bags at the Gold Coast show, which is going to be a lot more than 2 and 2, and then a computer can do the calculation for us. So I've defined some here. S is equal to 10, 7, 5, 11. So we've got Andy's and we've got Graham's show bag, and we've got Mars bars and cherry ripes. And a cost matrix, 0.55, 0.65 for Mars bars and cherry ripes. Now you'll note here that the vertical bit is the Mars bars and the cherry ripes, and now it's the horizontal bit here that is the Mars bars and the cherry ripes. And over here, that's our cost column, and here, this is our, for better term, who column. And I'm going to multiply these, and what's going to happen is it's going to actually kind of cancel out these two things, the types of chocolate, and it's going to give the who and the cost. So then we'll be able to see how much it cost for Andy and Graham. So this is the process. We wanted, remember what we did earlier, we wanted 10 and 7 to be multiplied by 0.55 and 0.65 like this. And then we wanted 5 and 11 to be multiplied by those as well, like this. And then we could get our final cost. This is our useful process of doing matrix multiplication. And I'll be more specific in a minute, but I want you to really stop. You can pause the video again and have a think about what's just happened there. And have we just done a straight 10 times 0.55 and 7 times 0.55? No, that didn't make sense. What we've done is a horizontal multiplied by vertical type multiplication. So have a think about that for a minute, and then I'll show you the procedure. You're interested to know that over on the side here is the total profit. Just adding in another layer, and that is to do our profit matrix and subtract S times C. Remember when we've defined this as S? Oh, that's not what I wanted to do. Go to highlighter. We defined this as S and this is C, so we've got S times C. And that gave us our overall profit. So there we go, matrices again. We can do that mathematically, take them out of the context and deal with the mathematics. So, let's have a look at a worked example. We've got A and C. We're going to calculate A times C and C times A, doing the same process. And then I'm going to get you to do that as well. So, let's start with A. A times C is equal to 3, negative 1, 2, 7, times by 4, 2, like that. Now, as we did earlier, we had 3 times 4, and then we had negative 1 times 2. We sort of worked horizontally and multiplied by the vertical bits. Negative 1 times 2, and we've got a plus there. So this is just one single term. And our second one is going to be, I'll put a little bracket around this, I don't have to, but it does help me to see what's going on. Second one is going to be 2 times 4, and then 7 times 2. And again with a plus. So 2 times 4 plus 7 times 2, bracket, and I can simplify this. 3 times 4 is 12, minus 2 is 10, 2 times 4 is 8, plus 14 is 22. So there's the result of A times C. And that's all good, and that's all we need to do. This doesn't have a context though, so you won't be able to see, well, what does this mean for chocolates and bags and things like that. There's no context here, it's just a theoretical answer. So that's our first one, A times C. Part B is C times A, which is 4, 2 times by 3, negative 1, 2, 7. Now this time we can do our 4 times 3, but then what do we multiply 2 by? There's nothing there. And actually what we've got is called a dimension mismatch. We don't have a 2 by 2 in the internal dimension set, which means we can't do that multiplication. So beware in your exam and in the textbook and other places of little questions that ask, can you multiply C by A? And think about the dimensions. For multiplication to happen, the dimensions must match. Okay, so now it's your turn, and I'm going to build into this video a couple of minutes for you to actually have a play and see how you go with this question. So here you go now. Okay, great job. Hopefully it went well. And I'm going to put up 2 solutions and we'll see how you go with those 2 solutions. So A is x times y. And keep in mind we've got to look out for those dimension mismatches. 3, negative 1, 4, 9 times by y, which is negative 1, 4. And that's equal to 3 times negative 1. I'll put it in brackets again just to be careful. And then negative 1 times 4. And then 4 times negative 1, and then 9 times 4, and then we get 3 times negative 1 is negative 3, I'll slow it down here, and then negative 1 times 4 is negative 4, and then negative 4 here, and 36 with a plus in the middle, and that of course is equal to negative 732. So hopefully you got negative 732, but if not, just check what you're doing there, and you could always actually email me a photo of the work you did and I can help you identify where your problem might have been if you did have a problem. Okay, now the next one is 2x times y. I've not snuck in a sneaky dimension mismatch here. What I've asked you to do is a scalar multiple and a matrix multiple at the same time. So 2x times y is going to be 2 times 3, negative 1, 4, 9 times negative 1, 4. Now in this case, it actually turns out that we would typically do the multiplication in the order it arrives. That's how the order of operation works. But multiplication is called commutative, and you don't have to worry about what that means. But what I'm going to tell you is that it doesn't matter what order we multiply things in. So I could actually multiply, because particularly since I've already done this, in the previous question I could multiply those 2 together and then just multiply everything by 2. So it should be equal to this thing times 2. But let's do it the normal way first, which would be we now get 6, negative 2, 8, 18. I've just multiplied the first matrix by 2, negative 1, 4. Then I'll do this multiplication, which is 6 times negative 1 plus negative 2 times 4, and then 8 times negative 1 plus 18 times 4. And that will be equal to negative 6 minus 8, which is negative 14. and then negative 8 plus 72, which is 64. And you can check me if you want, but there's my answer, which is this times 2. So that's good. We could have done this first. But of course, with the brackets being there, no, it's always handy to do the brackets first. So I'll put that one there just for you to think about, and hopefully you came out with that answer. Okay, so we're going to talk a little bit about matrix multiplication generally now. And I've only done this for a 2 by 2, but this works for any dimensions, as long as you've got that dimension matching, which we'll summarise at the end of this video. So here's my diagram. It's a really procedural process, but it's hard to demonstrate visually. So this is the best I could do. And basically, if you do a 2 by 2 multiplied by a 2 by 2, this is the result. You start with the yellow. So I'm over here. Okay, we get the top row multiplied by the first column, and that gives us cell 1, 1. So it gives us a yellow cell, the top row, first column of our answer. And then in light blue over here, we do the top row by the second column, and that gives us the top row, second column of our answer. So you can see where the light blue is in my solution there. Keep in mind my solution is this guy right in the middle. Okay, then we do the bottom row in green multiplied by the first column, and that gives us the bottom row, first column of our answer. And then we do the bottom row multiplied by the last column, it gives us the bottom row, last column of our answer. Would you believe it? So this is where we're getting a really nice process to follow. But you have to remember, if you've got to be in the game for a fair while. There's some calculations there. There's 8 multiplications, 4 additions, and you've got to do all this. You've got to be copying down the right numbers, making sure that things are in the right order. So be really careful about your approach to this and make sure that you're really clinical about it. And that's what this exercise is going to be about. You practicing being clinical about it to make sure that you get it right. So you could pause here, or it's actually on the OneNote, so you can access this diagram in the OneNote. Jump on and have a look at it. And just keep in mind it's a really procedural procedure. Is that a good way of saying it? I don't know. Anyway, here's another my turn, your turn. And I might even just create a little bit of space here for this. I think I'm creating a bit of space. There we go. Okay, so we've got worked example. A, B and C are shown there. Now A is a 2 by 2, B is a 2 by 3 and C is a 2 by 1. Calculate where you can AB, BC and CA. So let's have a look at how I would go about this. Again, I was really hoping to do this in class where I could have asked you guys some of these things, but alas, here we are. A times B is equal to 3, negative 1, 2, 7 times 0, 4, negative 3, 2, 0, 8. Now remember, we have to worry about dimension matching. So I need the first value there to be able to multiply by the top value of that cell, and the second value to multiply by the second value of that cell, and I've run out of values in both the column and the row that I'm dealing with. So this works, and we've got 2 here and 2 there, they're my dimensions. In fact, I could write down that A is a 2 by 2 and B is a 2 by 3, and the 2 there, the number of columns, matches the number of rows. The internal dimensions there are matching, and therefore this will work. So let's go through and do this calculation now. So 3 times 0, I might just move it down. We'll deal with having space. 3 times 0 and negative 1 times 2. Clever with buckets here. Now I'm going to work across. So this is my first cell in the top row, and then I get 3 negative 1 times 4, 0 here. So I'm doing there. I might just make that guy green so I can refer to it. Oh, I've really mucked this up, haven't I? There we go. And green. And then I'll make this guy green as well, so you can see what I'm looking at as I go. So my next one is going to be 3 times 4 plus negative 1 times 0. That 0 is nice, simplifies things. And then we get 3 times negative 3 plus negative 1 times 8. And in the second column, or the second row, sorry, I've got 2 and 7. Same thing again, but I won't worry about colours this time. 2 times 0 plus 7 times 2, 2 times 4 plus 7 times 0, and 2 times negative 3 plus 7 times 8. You can see how you've got to be really, really clear and clinical about your approach. Now I can calculate them. 3 times 0, I've got negative 2 there, 12 there, negative 9 minus 8 is negative 17, 14 here, I've got 8 plus 0, so that's 8, and then negative 6 plus 7 times 8 is 56, so that's 50. Close those brackets, and there's my answer. Now you'll notice here, and again, I would have loved for you to be able to come to this conclusion yourself, and maybe you have, but you'll notice here that the 2 and 2 need to match. They kind of cancel each other out, and I'm left with 2 and 3, and this guy is a 2 by 3 matrix. The answer, the result, is a 2 by 3 matrix. Isn't that really good? Now let's go on to B and C, and I can tell you now it's going to be pretty quick, because B times C is 0, 4, negative 3, 2, 0, 8 times by 4, 2, and we've got a dimension mismatch. 3 there, 2 there. So this won't work. We can't multiply them because the number of columns in the first one has to match the number of rows in the second one, and it doesn't. Multiplication doesn't exist. And C is CA, which is 4, 2 times by A, which is 3, negative 1, 2, 7. And again, we've got a dimension mismatch, 1 by 2. So we won't get a solution here either, and that is not possible. Okay, so here's the your turn, and I'll zoom out a little bit so you can see the whole of my solution, and you've heard me talking about it. So I'm going to give you 3 minutes to do this one. Good luck. Okay, so well done on that 3 minutes. I'm going to zoom across here and quickly do some solutions for you. The solution to A, x times y, is 3, negative 1, 4, 9 times by -1, 0, 2, 3, 0, 7, and hopefully you recognise that this has a 2 by 3 dimension mismatch. That doesn't work. So we can't multiply these two. Maybe you make a comment there. B is y times x. So we've got -1, 0, 2, 3, 0, 7 times by 3, -1, 4, 9. And y and x, well, we've got a 2 by 2 and then we've got a 3 by 2. And so we're going to have a dimension match here. This is good news. We've got 2 by 2. So we can do this calculation and it's going to look like this. And I'll highlight things again. We've got yellow multiplying by yellow and green multiplying by green. So there's our first one, which is -1 times 3 plus 0 times 4. When you're doing this process, any zeros that pop up in your matrices, they're just like gold. And then we have -1 times by -1 plus 0 times 9. So this is our yellow and this is our green here. And we're going to get the same thing going on here. So I'll highlight these and now let's work down. So our next one is going to be 2 times 3 plus 3 times 4. And then 2 times -1 plus 3 times 9. And then we've got 0 times 3 plus 7 times 4. And then 0 times -1 plus 7 times 9. And this is going to be -3, 1, because a negative times a negative is positive. And then we've got 6 and 12 makes 18. -2 and 18 makes 16. Then we have 28 and then we have 63. And there's my resultant matrices. So hopefully you got that. Or maybe you snuck a little mistake in there or two, and just check over that and make sure that you're being really clinical in your working. Okay, so I'll zoom back out now. The last one is C. C is YZ, and YZ is -1, 0, 2, 3, and then 0, 7, times by Z, which is -1, 4. And in this case, we check our dimensions. It's 2 and 2, so this will work, which is really good news. Still in pink there, so I'm going to zoom in and we'll do this calculation now. So I get -1 times -1, and then 0 times 4, and then I get 2 times -1, and then 3 times 4, and then I get 0 times -1, and 7 times 4. And this comes out as 1, oh there should be plus, sorry, we're adding those terms together, my apologies. 1 plus 0, -2 plus 12, which is 10, and then 0 plus 28. Now interestingly, my result here is a 3, just picked orange, so I'll try that again. It's a 3 by 1, and we started with a 3 by 2 and a 2 by 1. And the 2's kind of cancel out, they cancel each other out, and we're left with a 3 by 1. Isn't that amazing? A really interesting trait that we get from that. Now I did take this question a bit further, which is why I gave you 3 minutes, and hopefully you used it well, or maybe you paused and took a bit of extra time, which is fine. Can you explain what is interesting about the result? Well, I think this was geared towards me leading you in class towards this idea that I've just spoken about. 3 times 1 is the resultant thing. So and I've got a summary of this lower down, but it's interesting that you can calculate the value or what the resultant matrix will look like. And then we had this question here. Can you calculate y, x, z? Now, it doesn't actually ask you to calculate it, but I will write down an answer for it in a moment. But y, x, z, well, let's have a quick look at whether we can calculate it. I'm going to bring it down here. So y, x, z. Keep in mind that y is, well, it's not equal to, so that's probably not the right symbol, but y is a 3 by 2. So I'll put a little arrow, 3 by 2, x is a 2 by 2, and then z is a 2 by 1. Is that right? 2 by 2? Yep, perfect. So yxz is going to be a 3 by 2 multiplied by a 2 by 2 multiplied by a 2 by 1. So technically, as long as the internal dimensions match. 3 by 2 here, times by 2 by 2 will give us a 3 by 2 result. And then, if we bring down this guy, we get times by 2 by 1. And then we get 3 by 2 times 2 by 1. 2 by 2 works, and we get a 3 by 1. So isn't that really good? So it works, and the answer is y, x, z. We've done some of this work already. So yx is -1, 0, 2, 3, 0, 7 times by 3, -1, 4, 9. So that's being a bit funny. And times by z, which is -1, 4, 3, -1 there. We've already done yx, which gives us -3, 1, 18, 16, 28, 63. And we multiply that by -1, 4. And we can do that multiplication. And I'm going to do it really quickly, and I'm sorry to rush, but my computer's running out of battery. So -3 times -1 is 3. 1 times 4, that makes 7. 18 times -1, -18. And then 16 times 4 is 64. So it's 54, 46, I believe. Correct me if I'm wrong. 28. And then 4 times 63 is 252. Minus 28 is 232, 224. So there is the value of yxz, and I got that by doing y times x. So I did this one. Oh, that's not what's meant to happen. Just went to my yellow highlighter. My apologies. It's not swapping to highlighter. Here we go. I think I'm there, and it's rubbed some stuff out. Did those two to get this, and then I multiplied by z to get my final answer. So this should be it. Oh, it's not changing pen colours. Okay, let's just go to my rules for multiplication, and then I'll show you the questions you can do. So, for a times b, a must have the same number of, now keep in mind what we said before, columns as b has rows. And that swaps obviously if it's b times a. And we've got our summary here. So as a is an m by n matrix and b is an m by p matrix, then the n's kind of cancel out. We end up with the result being c, an m by p matrix. A times b and b times a only exist if they're both square. So both are square. So if they're not square, my writing is a bit funny at the moment, so it's just being a bit laggy. If they're not both square, well then you might have a times b, but then you definitely won't have b times a. And you can have a think about that if you want. A squared, we haven't quite got to a squared yet, but a squared only exists if it's a square matrix as well. Otherwise you will not have a dimension matching. If a is square, I should have written. And if a is an m by n matrix and b is an m by p matrix, then a times b is an m by p matrix. So these are all the rules, and I would suggest you come back and have a read of these again once you've done some questions. They'll probably make a little bit more sense. Anyway, we're on to 8e, and you can do these multiplication only questions. Question 1, 3, 4 and 7 from exercise 8e now. But try some and ask questions if you need to, or go back and watch this video again. All the best.